Here we go. Welcome to lecture number 5, I think. I want to just put something up and I'm just going to apologize in advance. If you're a surfer or like surfboards, the following footage might be slightly distressing to you. So I just apologize for that. So let me just share my screen. So here we go. Can everybody see this? Now, let me play this and then I'll go and ask some questions about this. So you'll see me here. I'm wearing my safety glasses. You can already probably tell what's going to happen. It's only very short. You should probably put your sound on. Here we go. Now, did everybody hear that sound? Oh, I can't see where my chat is. Here's my chat. Okay, let me play that again, just for the fun of it. There's a couple of things to notice in this video, obviously. One is, this is in my lab. Obviously, a saw is no match for a surfboard. We actually needed to cut the surfboard down. But you know, I always talk about safety. What could I have done better in terms of safety? I mean, I'm obviously wearing the glasses, so I'm doing that. Is there anything else that I could have done better? You can just type it in the chat. Obviously, not cut the surfboard might be one of them too, if you don't like cutting surfboards. Standing on the bench, when I watched that video, the footing, if you look actually in that last video, I actually had to grab the windowsill to actually get down. It was a little bit high. What about gloves? Should I have worn gloves? What about a face mask? Yeah, there you go, face mask. That probably would have been a better idea. So let me stop sharing that and I'll show you another video that I did that. Where is that? Is that even up here? Let me just quickly go to that. Close that again, and I'll actually show you where I've done something like this, but I've actually used a bit better safety gear. And again, you might find this distressing if you like surfboards. So can everybody see this screen from YouTube? So you can already see face masks, earmuffs, some form of head protection, glasses. I've got a full covered shirt. I've got something in the back here. I'm not standing on a bench. So this is something I recorded last year. So I'll just let it run and you can probably see what I'm going to do. Again, I apologize if you like surfboards.
Wales is in lockdown and I haven't been able to get close to my lab, but that doesn't mean that I can still torture a surfboard at home to check what is inside. So give me a second and we'll get started.
So you can obviously see that my safety gear is a lot better. I'm wearing gloves. I didn't stand in the path of the fibers. You did actually see that the fibers were flowing somewhere over my lawn. I've got my nice face mask on, earmuffs, gloves. I'm wearing protective shoes, covered shirt. So this is probably a lot better. This is, by the way, is not just pure destruction. We are this afternoon going to talk about polyurethane, which is what is inside the core of this particular surfboard. And polyurethane is a major industrial application. Refresh the tap. Oh yes, let me do that. Refresh the tap. Love it. Another subscriber.
As you know, New South Wales.
You don't have to listen to me again. By the way, that other video that I showed of me cutting the surfboard, I put it up on YouTube on Friday because we did it in the lab on Friday. When I woke up on Saturday morning, I had 4,000 views. I'm amazed at that because there's really nothing in it other than me just cutting the surfboard. So let me stop sharing this and actually go back to what we were doing. So all of this is in a way related to what we were actually trying to do. It's all about molecules, it's about polymers. And of course, I have to admit, I do like cutting surfboards in half, in particular, if they are broken. And I also got a little bit of karma because I broke one of my surfboards on Saturday in the surf. So I cut one down in the lab, and on Saturday I broke it in a swell, which wasn't good, but it means it's going to live on in the lab when I do a bit more testing on it. Hang on, this is the wrong one. So I'm too excited with all of this surfboard stuff going on. So here we go. This is the one that we need to put up. Go back to Zoom. In a class, this would have been a lot easier. So just checking, and thank you for the subscribing. You can see the slides, I'm hoping. Just if someone can tap yes in the chat, because this is where we left off. Oh, before I start, I should actually put this in here in the chat. I will go through the post-lab 1 quiz in the, I can't type, in the 12:30 p.m. lecture. And we'll also explain the peer assessment with the workshops. The peer assessment process, that is. So this is where we were. View, let me go to page display. Where's my full screen mode? Here we go. It says my screen sharing has been paused. Is that right? What is going on? Can everybody see if I change the slides?
We can see that you're still on the formula weight slide.
Oh, okay. Hang on. It's not moving then. So gotta love the technology. Let's try this. Okay, if I change slides now, can you see that?
Yeah, we can see it. Yeah.
Yeah, cool. All right. So now I can go back to where we actually left off last weekend. Not last weekend, last week. I'll keep the chat line here. So we talked about formula weight. And this really has to do with how you calculate. If we go into the labs, you would sometimes ask to convert from grams to mole. So in order to do that, you really need to know what the formula weight is. In order to get our formula weight, you use the atomic mass of each of the elements and atoms, or the atoms that are in your molecular formula, and you sum them up together, and that gives you a value in atomic mass units, or AMU. And later we'll see that that then translates to also grams per moles. If we go and use ionic compounds, they usually fall into their most elemental substituents, or for example, with sodium chloride, it just falls into sodium and chloride ions. So for that case, you use the empirical formula. Now, last week, there was also a question as to what is the actual use of empirical formulas. And in a few slides, we're going to talk about that as well, to see, you know, what is the actual use of an empirical formula, and how can you use information about the ratio in the empirical formula and your molecular weight to then find out what the actual molecular formula is. So in the case of this example here from sulfuric acid, 2 hydrogens, 1 sulfur, 4 oxygens, we add together the atomic weight of the 2 hydrogens, 1 of the sulfurs, and 4 of the oxygens. And again, I apologize if you did chemistry at HSC level, but this is something that we need to talk through with the elemental, just to get the fundamentals correct, or not correct, but to talk through the fundamentals. So if you add all of that up and you do your bookkeeping correctly, you end up with 98.1 atomic mass units as the formula weight for sulfuric acid. Now, if we would go to a molecule, then obviously the formula weight is also called the molecular weight. So talking about glucose, which is an important molecule for us, as it helps with our body, the molecular weight of that, it contains of six carbons, 12 hydrogens, and 6 oxygens. So if we do our bookkeeping again and we add them all up, we'll get the atomic mass units of the carbons, the hydrogens, and the oxygens. And when we add them up together correctly, we end up with the 180 AMU. Now, if we, let's say we have a compound and you're gonna need to figure out how much is in there in terms of percentage, you can figure out the percentage element, or the how much of the percentage of the weight is made up by a certain element, let's say carbon and oxygen. You use this equation. So you take the number of atoms, say carbon, you multiply that by the atomic weight of carbon, and you divide that by the formula weight of the compound. And that gives you the ratio of your element over the compound. And hopefully there's an example coming up. So I mentioned carbon. So if we go back to glucose that we just looked at, there are 6 carbons in glucose. So the percentage of carbon in glucose can be calculated by taking these 6 carbons. Each of them has a mass of 12 AMUs divided by the formula weight for glucose, which we just saw was 180 AMUs. If we do that, 6 times 12 is obviously 72. You divide it by 180, you multiply by 100, and you get 40% in terms of the percentage of carbon in glucose. So if we now go, we want to link the AMU to moles so that we can talk about how many grams there are in a mole, because it says here in the first bit, it says when we do work in the lab, we can't really work with an individual molecule because they're simply too small and they're also very, very light. So you would never actually handle a single molecule. There have been instances where, if, for example, you think about very advanced microscopy procedures, like many, many years ago, I was involved in a project where we were handling individual carbon nanotubes, which are objects that are micrometer scale. So it's at least you have some chance of actually seeing them in a microscope, and we were able to pick them up with some very sophisticated tweezers. But with a water molecule, you'll have absolutely no chance of doing that. So if we are actually going to talk about things and compounds, then we use something that is called Avogadro's number. So when we're in the lab, you might take 20 grams of water, and that's roughly equal to a little bit more than 1 mole, because the Avogadro's number actually links the AMUs to the grams, because we say that if we have 1 mole is then defined as the amount of particles that you can find exactly in 12 grams of carbon 12. Remember, carbon 12 is an isotope, but it's the most abundantly available isotope of carbon. Now, this was a definition that was valid up until a couple of years ago. And Avogadro's number is equal to roughly 6 times 10 to the 23 atoms or molecules in 1 mole. And 1 mole is then equal to the amount of grams, or will be your AMU. So normally if we take water, we got 2 hydrogens weighing 1, we got an oxygen weighing 16 together. The formula weight of water is 18 AMU. if we now take a mole of that water, then we simply say that the molecular weight of water is now 18 grams. So we do away with the AMU and we convert that to grams per mole. But you would always calculate the molecular weight in grams by using the same procedure that you would do to calculate your formula weight. So that was the definition that was in use until a couple of years ago. I mentioned this at the start, that this Bureau International des Poids Mesures, if that's the correct pronunciation, they came up with this new definition in 2019, and they simply defined exactly what the elementary entities are in a mole. And they've now defined it exactly as Avogadro's number, which is 6 point, I'll let you read all the digit yourself, times 10 to the 23. So in essence, nothing has really changed about Avogadro's number. The only change is that it is now precisely defined. They said, okay, this is what we are defining Avogadro's number. And Avogadro's number is obviously important in our calculations. So I've already mentioned this. It's the molar mass is really what we mean is like the mass of a mole of a substance. And with that, we mean the grams per mole. So a mole of oxygen, which is quite a lot of a volume if you take into account that the oxygen is a gas obviously occupies a lot more space than what liquid and solid would be. If we take a mole of oxygen, the formula weight for oxygen contains, we need to add together the mass of the two oxygens. That gives us about 32 grams. If we take a mole of water, which is equal to about 18 milliliters of water, because you know 18 milliliters of water is about 18 grams. 18 grams is what the formula weight would be for water in the liquid state. And then if we take a solid, so we take a salt, which we would use, if we add these up together, we then get the mass is then of sodium and chlorine. It's a solid. It has a weight of about 58.45 grams. So we can link the grams to the moles. And one of the things I said on the last slide, that the formula weight, which we work out, in AMU, will be the same number as the molecular mass in grams per mole. Well, you can do, there's a message, wouldn't it be easier to weigh liquid oxygen? It's not about, you might be able to weigh 32 grams, but if you want to know what, let's say, 1 million moles is, then it becomes harder to weigh those things. So it's better to just work it out and calculate it. These examples here are just for illustration. So if we now go and have a look at these moles and how we use it, if we look at this first line, it says atomic nitrogen, which is just N, has a formula weight of 14 AMUs. It has a molar mass now of 14 grams per mole. And there is, in that 1 mole, there is Avogadro's number present. So roughly 6.02 times 10 to the 3 atomic nitrogen atoms. If we take molecular nitrogen like it exists around us, like in the atmosphere, we would have nitrogen exists as the molecule. So it has 2 nitrogens. We know that the formula weight is 28. We know that the molar mass is 28. In terms of the amount of molecules, 1 mole will contain 6.02 times 10 to the 23 nitrogen molecules. Of course, in a molecule, there is twice the amount of atoms. So it would be 2 times Avogadro's number in terms of atoms. If we go to silver, it has a formula weight that is 108 roughly, and it also contains 1 mole of silver ions. If we look at, say, barium chloride, which has the formula BaCl2, so 1 barium, 2 chlorines. We know what the formula weight is. We know what the molar mass is. Then we know that it contains Avogadro's number in terms of the molecule, but it also contains roughly 1 plus 2 is 3 times Avogadro's number in terms of the total amount of ions that you have present. So we can use Avogadro's number to figure out how many elementary entities we have present. So one of the things which I think you did in the workshops, and which is also important when we do work in the lab, is to go from grams to moles to formula units. So you might be given something, this is so many grams of this molecule, how much is it actually in formula units. So for example, if you're being asked how many atoms are there in 3 grams of copper. So you start off with your grams, so you have 3 grams, then we use the molar mass of copper, which is 63.5, to go from grams to moles. In order to go from grams to moles, we divide by the molecular weight. So the molecular weight of copper is 63.5 grams per mole. So if we divide 3 by 65, then we get how many moles we have. In order to go from moles to the formula unit, or to actually find out how many atoms of copper we have, we then multiply that by Avogadro's numbers, which tells us that there is roughly 6 times 10 to the 23 atoms per mole available. So if we multiply 3, if we take 3 divided by 63.5, multiply that ratio by Avogadro's number, we then end up with a value that in 3 grams of copper, we can expect to find 3 times 10 to the 22 atoms. You can also do this, as I always mention, it's just a bookkeeping exercise, so you can apply this to any sort of fictitious element. Let's say we have a fictitious element that is called a rock with the symbol RK. We know that the element, the rock, likes iron. We also know it's pretty solid in appearance, and we know that the rough mass in terms of the molar quantity of the rock is about 118 kilograms per mole. So if the question is, how many atoms are there in 1 kilogram of the rock, of the element, the rock, then we would take our 1 kilogram, we would divide it by the molar mass, which is 118 kilograms this time, not grams, and we would multiply that by Avogadro's number. And that gives us then that there are 5 times 10 to the 21 atoms in the element of the rock. So the element itself doesn't matter. You can call it whatever you want. This is not chemistry. This is essentially just doing calculations and keeping track of what you're doing. So in a case, it's bookkeeping. That's why Mr. The Rock is here. So it doesn't matter what we're, don't be confused by all these different names. You can look at this in a very objective way. So here is where we can also now start linking what actually the use was of our empirical formula. So let's say you're given some information about the mass percentage of the elements, and you need to figure out what your empirical formula is. So you can do that in a number of steps. So we want to go from the mass percentage of the element. So you might be given that there is, we'll see in an example that, 10% carbon, 20% oxygen, 10% hydrogen, and then you got to figure out what is the empirical formula. Now, remember from what we talked about before, the empirical formula is the ratio of the elements with the smallest division. So if we have 2 carbons and 2 hydrogens, if that's the molecular formula, then the empirical formula is 1 carbon and 1 hydrogen. So we can go in these 3 little steps, or not 3 little steps, in 3 steps. The first step would be if we have, for example, para-aminobenzoic acid, which according to this information is sometimes present in sunscreen. And we are getting the information that it contains 60% carbon, 5% hydrogen, 10% nitrogen, and 23% oxygen with some additional values. We're being asked, what is the empirical formula of PABA? So the next thing, so this is a step 1. We need to gather this particular type of information. If we go to the next step, we're just going to assume, okay, we have 100 grams of this. So if we have 100 grams, we can use the percentage to work out how many grams we have. And we can use the formula weight, or the molecular weight of each of these elements to work out how many moles we have. So carbon, we know, has a molecular weight of 12 grams per mole. So if we got 61.31 grams, which we got by multiplying the percentage and assuming we've got 100 grams present, we end up with about 5 moles of carbon. We can do the same for hydrogen, we can do the same for nitrogen, and we can do the same for oxygen. In each of these cases, we use the molecular weight information. So we can then go to step 3 by calculating the ratio by using the smallest number of moles. So if I go back a slide again, I'm going the wrong way. If I go back up again, the smallest number of moles that we have, so we're just going to normalize it to 1. So if we have the smallest number of moles of nitrogen is that, if I'm going to set this to 1, I have to divide everything by 0.7288, which is what we do in step 3. So I take carbon, of which we have roughly 5 moles, and I divide it by the smallest number of moles, which was for nitrogen, 0.7288. That gives me roughly a number of 7. If I do it with hydrogen, it gives me a number of 7. If I do it with nitrogen, that's obviously what we're normalizing to, I get a number of 1. And if we do it with oxygen, we roughly get a value of 2. So now we have ratios of carbon, hydrogen, nitrogen, and oxygen. So there are 7 equivalents of carbon, 7 equivalents of hydrogen, 1 equivalent of nitrogen, and 2 equivalents of oxygen. So that means if we now convert this to the empirical formula, you get that the empirical formula is C7H7NO2. And then Bob is your uncle because now you figure out what your empirical formula is. Now, the next step that you need, now that you have your empirical formula, if we now know what the molar mass is, or the molecular weight of the compound that we're after, then we can figure out the molecular formula. And that's what we can do next. So, for example, if we know that we do this analysis and we get that the empirical formula of a compound is 1 carbon and 1 hydrogen, that has a molecular mass of 78 grams per mole. What is it molecular formula? So if we now know that the total mass is that, we have a whole mass, we know what the molar mass is, which is 78 grams per mole. So we can then look at what is the multiple of CH compared to 78. So if we have 78 grams per mole, we know that's the molecular weight. We know the empirical formula is CH, so 1 carbon, 1 hydrogen. We know that we can add them together and we get about 13. So using the molecular weights of the elements. So a carbon is obviously 12 grams, a hydrogen is 1 gram. And then we simply do a bookkeeping in and we divide by that and we get a value of 6. So we know that the molecular formula is then C6H6. The empirical formula is obviously CH, but we can use information about our molecular weight to work this out. So how do you actually get some of these information, which is what you can do routinely by something that is called combustion analysis. So you would have a furnace. In the furnace, you would put the material that you're interested in, you feed in oxygen, and you burn it, and then you analyze what comes out. So you have something that will indicate how much water is produced. And then you have another indicator that tells you how much of your carbon dioxide is produced. And then it allows you to figure out what you've got present in your combustion chamber. So we know that the mass of carbon can be determined from the amount of carbon dioxide. Hydrogen you can get from your water production, and then oxygen you can then look at the difference of the masses between your hydrogen and your carbon dioxide. Now, you need to be aware of this when you look at this, that it's always harder to determine how much of the oxygen you have, for the very simple and obvious reason we're actually feeding in oxygen at the start of this. So it's not that easy to get the oxygen. You need to do something different for that. So the way to do this is to do another, what I would call bookkeeping exercise, where we start off with the mass of carbon dioxide produced. So this comes out of our absorber here. We then can convert the mass in grams using the molecular mass of carbon dioxide. 1 carbon, 2 oxygens gives us about 44 grams per mole. That leads us to moles produced. We can then use information about the ratio of the carbons versus the oxygens in carbon dioxide. So we know there is 1 carbon atom per carbon dioxide molecule. Then we know what the moles is of our original sample, and that leads us to the mass of carbon in what we were after in our original sample. So obviously for carbon dioxide, this is really simple to do, but we also routinely do this analysis on large proteins, which have gazillions of carbons in there, other types of polymer. So there is actually, this is a very useful method to find out what is present. We can use a similar approach with the mass of water produced. So we know how much of our water is produced from what is trapped here in these absorbers. We use the molecular mass. We look at the moles. We now know that we've got 2 hydrogen atoms per water molecule, and then we work out what our mass is in the original sample. You can also get some quantitative information if we look at our balanced equation. So balanced equations are always a good way to look at what you've got, what happens on the molecular scale, and then you can also look at what happens when you go down to the moles. So in a chemical equation, which is what we would normally write and what you've been practicing in the first lab and the first workshop. So we have, if we add 2 hydrogens with 1 oxygen, we produce 2 water. So we produce water liquid when we combine these. If we go and look at the molecular formula, we have, like I said, 2 molecules of hydrogen, 1 molecule of oxygen gives us 2 molecules of water. If we now go to the moles, that means if I've got 2 moles of hydrogen, 1 mole of oxygen, I get 2 moles of water. And now you can use your information about the molar mass and you can convert to grams. So if I take 2 moles of hydrogen, that is about 4 grams of hydrogen. 1 mole of oxygen is equal to 32 grams, and 2 moles of water is equal to 36 grams. one of the things that it says here in this little diagram is that notice the conservation of mass. We can't really make mass and we can't really destroy mass. So if we started with a total of 36 on the reactant side, if we capture everything that happens in this reaction, then we would need to have 36 grams on the other side. And if there was heat or something else happening and some molecules might evaporate, if you do this in an enclosed chamber, then you can always find exactly what the mass is that you have present. And that sort of leads me into something that is called stoichiometric concentration. And that's where you use coefficients in the reaction. Again, stoichiometry, you're probably getting sick of telling this. It is really still bookkeeping. We can use stoichiometric calculations to go from grams using the molar mass to our moles. Then we use a balanced equation, which is where our stoichiometry come in. Stoichiometry just tells us how the moles compare in the balanced equation. And then we can then eventually end up with our grams of substance B. So stoichiometry is another example of our bookkeeping. So these things are usually best illustrated if we look at an example. So question could be how much water in terms of grams can you produce of water? How many grams of water can you produce if you take 1 gram of glucose? We know glucose is C6H12O6. It has a molecular weight of 180 grams per mole. So the first thing we would need to do is to look at the molecular equation or the chemical equation. We know that 1 mole of our C6 of our glucose, which is solid, if we burn that in the presence of gas, of oxygen, or we add oxygen to that, that will produce us carbon dioxide and water. So we know in order for this to balance so that we have the same amount of atoms on the reactant side as the product side, we need to change these soups. We need to balance this, which is what you do in terms of your stoichiometry. We also know, we've been given the information that we've got 1 gram of glucose as a start. So in order to end up with our information as to how many grams of water can be produced, first step we have to do is to go from grams to moles. And we can do that by dividing the gram of glucose by its molecular weight. And the molecular weight is 180. So we can then end up with our moles. So we also know, if I go back this equation, that if I have 1 mole of glucose or 1 unit of glucose, it's going to produce 6 units of water. So if I know how many moles of glucose I have, then I know that the moles of water is about 6 times that. So, and this particular mole ratio, so I know 1 mole of glucose gives me 6 moles of water. This is what comes from this balanced equation. And this is where we get what we refer to as stoichiometry. So 1 over 180 moles of glucose produces 6 over 180 moles of water. I haven't worked out how much that is, but you can obviously work that out yourself. So the last simple step is then to use your molecular weight information about water to then figure out how many grams of water you have. So if we know we have 6 over 180 moles of water, we multiply that by the molecular weight of water, then you get at about 0.6 grams of water. So you go from the grams of glucose, you work out what the moles of your glucose is, you use the ratio, the stoichiometry stoichiometric ratio of glucose to water. Then you get your moles of water. You multiply it by the molecular weight of water, which gives you your grams of water. So in the next chapter, or in the next bit of the lecture that we're going to look at, not today, but next week, we are also going to look at heat. And this is where our stoichiometry will come back as well, because if we're going to work out heat in terms of enthalpy and even entropy and all these different types of thermodynamic concepts and heat or thermochemistry concepts, then we're going to have to work out, we have to use our stoichiometry and work out what these values are. But that's something that we're going to look at next week when we start on thermochemistry. One other aspect that we need to be aware of is that you can have something that is called a limiting reactant. And a limiting reactant is like a bottleneck. The bottleneck will determine how much you can produce. And this is very important because, again, you need to know your information about the stoichiometry. If you want to think of it in a different way, it's written here where it says it's really a limiting reactant is the thing that you disappear at the first time. So if we look here at our reaction, we have 10 hydrogens, 7 oxygens, gives us 10 water molecules and 2 oxygen molecules and no hydrogen molecules. This is before the reaction. This is after the reaction. So if we look at the calculations, what we're ended up with is that we now have an excess reagent, because before and after the reaction, we still have some of our oxygen present. So that means that the oxygen that we started with, not all of this has reacted away. And you may notice that we have no hydrogen molecules after the reactants. So if you don't think of it, so we've lost all our hydrogens, we still have some oxygens. So that would indicate then that our nitrogen is the limiting reactant. Sorry, the hydrogen is the limiting reactant. So we can only produce as much water as is determined by the stoichiometric ratio between the production of water and the reacting of the hydrogens. So that really determines how much we can have. Some other terms that I need to throw out to you is theoretical yield. This comes up a lot in organic chemistry, where you might be making something new, a new compound, and you do all your bookkeeping, you use all your stoichiometry, and then you work out that in theory, I can produce this amount of a particular compound. However, it can be very different from what actually happens in when you do something due to various reasons that can go wrong in the chemistry of what you're doing in the lab. So there's also, you rarely end up with 100% of your theoretical yield. One of the things that comes up, where this comes up all the time, is if you think about conversion of, and you can think about conversion in solar energy, right? So we know how much power the sun can deliver. Solar panels can only convert a certain amount of that into actual electrical energy. Some other bits might be lost through heat and all sort of various other bits. So it's the difference between the actual thing that you can calculate and the maximum that you could produce. So to give you an example, years ago, this is a long time ago, when I attended some talks about solar conversion, these were all these people that worked on these solar conversion technologies in the lab, so not on solar panels. And people there got very enthusiastic because they had an actual yield, so a conversion efficiency of 5.4%, which means 94.7% was lost in terms of the conversion process. So I raised my hand, obviously being completely ignorant, and I said, why is this so exciting? But apparently that was state of the art. So what you get in terms of actual yield might be very different from what you can produce in theoretical yield. And the same goes, but obviously there's a much better yield when you go and look at combustion engines. They're very efficient ways, I believe, in terms of converting what you produce to what you can use when you drive your car forward. And obviously, well, I keep saying obviously a lot, but the percentage yield is actually worked out by looking at what you actually made, how much did you make versus what you thought you could make if everything was in an ideal world. Molarity is something that would have come up. Molarity is what we measure, what the concentration is if we need to make something. So in the labs, you would have been handling, let's say, hydrochloric acid at 1 mole per liter, and we refer to that as the molarity. And it's also, we usually have the symbol capital M to indicate that we're talking about molarity. So it's the moles of a particular solute. This can be hydrochloric acid in the volume of the solution in liters. So it could be 1 mole per liter. And you can use this obviously to go between liters and moles. These are all different types of concepts that we've been using in calculations. So mixing, we already did some of that in the lab. So we looked at things, if we want to make a particular type of solution, you need to have a known quantity of your solute. So for example, this is copper sulfate. You then, if you want to know exactly what we're going to use, you need to make a measure that is exactly defined. So if we use these 250 milliliter volumetric flasks in the lab, we looked at the precision of these. So we can make these up to a really high degree of precision. And then you can mix water up to that level and you swirl it together, and you've added exactly, or with a high precision, 39.9 grams of copper sulfate, assuming that your weighing balance is of high precision, and you put that in a volumetric flask of about 250 milliliters. So you have 0.25 moles in 250 milliliters. If you then swirl that together so that you get a nice mix, then you've made up a really good solution. One of the things that we'll be doing in the second lab is, and also the second lab is, we'll also have an online version of the second lab, which is where we filmed the experiment in the lab, and then where we ask you to answer questions of what you're actually going to do in the lab as well. So lab 2 is a little bit the relevance between the online version and the laboratory version. The face-to-face version is very similar at this time. So you can also do dilution, right? So you can take what is called now, let's say the original solution is our stock solution. I can take up 25 milliliter using these precise pipette. If you were in the face-to-face lab, we looked at the precision of these 25 milliliter pipettes, so they can be very precise. We put this into a volumetric flask, and then we add water. So what is happening is that obviously if we dilute something, the moles that we've added aren't going to change. The only thing that will change when we dilute something is that we have a larger amount of our solvent around it. And you can actually calculate these things, which will come up through some of in the question. So this is probably an important equation to be aware of. We know that the molarity of the new solution can be determined from the equation. So we have a molarity of our concentrated. We know what volume it's in, so it gives us our moles. Then we know that if we are going to dilute that, so say this is the bit that you initially pipetted, then you make it up to a larger volume. That means then you can work out what your molarity is of the new volume. So we know what the initial, so if I go back a slide, I know what the molarity is of the stock solution. I know what the volume is of my stock solution because I'm taking this up. I took up 25 milliliters. I'm going to put this into my new volume. So I know the exact new volume because I'm going to fix this up to about 250 mils. What I don't know is the concentration. So that's my only unknown. So my molar concentration of the original is known. My volume is known. I know my new volume. The only unknown is the molarity of the dilute solution. So you can just do that, work that out with a simple calculation. So this is a diagram on how we can use these stoichiometry. So we can go, for example, from the mass of a particular molecule, we can convert that to the moles. We then use the stoichiometry, so use coefficients from balance equation to go convert the moles of a substance A to a substance B. And then we can also work out what the volume is. So I've put this little bit here that I found that says, you know, keep calm, stoichiometry is easy. It's just that I find it a very strange name for something that is really should be bookkeeping, but that's just my opinion. The other bit that we're going to look at in the online lab of lab 1, you were shown some videos on titration. In the face-to-face version of the labs, I put way too much in there of what you could do. So there were some titrations in there. In the next bit, so laboratory class number 2, there will be some titrations that we're going to do. So you'll see videos of titrations of the actual experiment, and you'll also see, if you're in the lab, you're going to do some titrating. And titrating is really figuring out a method that you can calculate solutions of an unknown, because when we do titration, we use something where we have equivalence point or indicator change. So we put a molecule in there called an indicator that when it reaches a certain condition, in this case, it's going to be, it reaches an equivalence point and then it changes its color. So as soon as you reach a certain point, so by adding a number of molecules to it, it changes color, and then you can use information from how much you have added, the concentration, and information about the chemical formula to then figure out how much of the material you've got present. So that's a well-known chemical technique, which is called titrating. And in terms of titrating, is the flow diagram for this is we have a volume of a standard solution. A standard solution means this is how much we've got present, that we need to reach an equivalence point. The equivalence point tells you when the material is going to change color. So we need to use our molarity. Here comes our stoichiometry in place again, because we need to know what the balanced equation is. That then leads us to find what our moles of our solute in the unknown solution is. So we get moles. That's the first clue. Second bit is we know what the volume was of our unknown solution, which then gives us our concentration. So we go from volume to moles, use stoichiometry to get more moles, combine with the volume to get us the concentration. And that brings me to the end of this lecture. So we've now done, we looked at the nuclear model last week. We classified ionic molecular compounds. We wrote some chemical net ionic equations. There is another bit that I need to show from a question from last week, is to go through a net equation from the lab. Today we looked at mole concepts and stoichiometry. Last week we already looked at reaction types. This afternoon at 12:30, I'll talk about equations for the chemistry of major products, and I will also go through the correct answers for the post-lab quiz. Any questions? Okay, if all is good, then I see you all at 12:30. Take care. It is still dry where I am. So since we've been sitting behind the screen, please get up, stretch your legs, go outside, have a coffee, a tea, a glass of water, whatever makes you happy. Eat something. See you at 12:30. Take care.
Thank you.
Thank you.